We start with some the usual tensor that we learn about so far. So you learn in whatever your undergraduate classes that involve tensor, and those are most defined in the usual three-dimensional space. They start with vector in a three-dimensional space, and start with the most elementary description using Cartesian coordinate. And then using that to get the concept of what we call a tensor, at least in that space, and then generalize that either for a non-Cartesian coordinate. Generally, it doesn't have to be like spherical or cylindrical. Those are so-called curvilinear coordinate system. They still is not straight line, because coordinate is not straight line. But then the unit vector are all still orthogonal. But even more general is that the unit vectors are not orthogonal. You can still do that within a usual three-dimensional space. But then the concept can also be generalized to other space that is not the usual three-dimensional space, or you can add the time that the four dimension, you include time, and that allows you to do special relativity. And even more generally is going to non-Euclidean. So it means even in a three-dimensional space, you can use that to describe like a curved surface, a spherical surface, or whatever that you can use that kind of not on a non-Euclidean surface, use the same thing, or generalize that with time now, then the whole space is not Euclidean, or in that case, it's called non-Minkowski. So for special relativity, it's Minkowski space. If you even generalize from that, it's non-Minkowski. And that becomes a general relativity. We will not touch general relativity. We just get you the math preparation that if you look at general relativity, that gives you some of the basic preparation that you can understand, at least not scalable. General relativity is that it describes it as a tensor. And if you are scared, then don't worry. I mean, Einstein scared of that. He struggled with that for 10 years. You remember that? Special relativity is 1905, general relativity is 1915. So he struggled with math for 10 years. He has the idea for general relativity. And first, he's tried to generalize the case that special relativity is for a inertial frame. He tried to generalize this non-inertial frame. Then they pretty soon realized that what we call a non-inertial frame, it's just like having a gravitational field. And that is a famous equivalent principle. So whatever the acceleration you experience in a non-inertial frame, it's just like gravitational field. And that principle is just genius. It's just one very powerful idea that allows you to do general relativity and gravitational field, calculate, do all the formulation and to calculate the physical law, the express physical law in the gravitational field. And that is just a very powerful principle, but without the math, then you still don't know how to do it. They struggle for many, many years and ask his friends, mathematician friends, and ask about it all, learn about all these things. And one thing is tensor. And we generalize that to a curved space, that becomes what we call the Riemann geometry. Okay, and that is what is needed for general relativity. Without that, you just don't know how to express anything. Or even finally, you write down the equation you must. and otherwise, you don't know how to do it. You don't know how to express that. The idea of general additivity, although the principle is powerful, equivalent principle is very powerful, but without the math, you don't know how to do any calculation. So that is important, and the concept is start with what we call geometry. So we describe all the physical law within a certain geometry. Our assumption of the geometry, basically, we say the object that we try to describe, objects of geometry. It means that it doesn't depend on how we describe it. It's actually intrinsic, something intrinsic to the geometry. The simple example is a vector, right? So whatever, and the simplest example of a vector is spatial vector. So you have a point at a certain point A to point B, right? Then there's difference in the spatial location. We call it a vector, spatial vector, and so that one is geometric object. And then if I ask you to describe a vector, say I'll just give you a vector X, right? How you write it, how you describe X, how do you describe? Yeah, you need to choose a coordinate system, right? Because I just give you X, then how you write it down becomes impossible without a coordinate system. But the coordinate system is invented by you. You describe it. You choose an origin at the start, at the beginning of this vector, and then you choose unit vector, or the simplest case is obviously the Cartesian coordinate. You have a 3 unit vector along three lines. You have X, Y, Z, right? And then you define unit vector E sub X along this X direction, E sub Y, and then E sub Z, right? Once you do that, then the vector can be expressed using number, what we call coordinate, X, Y, Z, right? So the idea is you can write X equals to summation of the coordinate, what we call like X. Give you some index, like I. I'm using superscript for some reason, because later on we'll distinguish the superscript and subscript, and that is a little bit later. But well, start using this superscript for components. So I is from 1 to 3, right, for usual 3-dimensional space, and then the unit vector E and I, just some xi times E. The x1 is X, X superscript 2 is Y, X superscript 3 is Z, so it's X, Y, Z. So you write explicitly X, E, X, Y, E, Y. That's easy. Easy. Right? So that is how we describe a vector. But in doing so, we are introducing something that depends on your choice. And the idea of physics is that this thing, vector, or later on generalized to tensor, or scalar that doesn't have direction. It should not depend on your choice of coordinate system. But that is just we introduced by ourselves. So whatever the physical law or the principle of physics should not depend on the choice. It's okay. So that is the main idea. Say, if you choose another coordinate system, you can rotate. Say, the simplest change of coordinate system, just rotate it. You rotate it like you get x prime, y prime, or the direction is ex prime, and then ey prime, and then ez prime. Just rotate your coordinate system, and then you can write it down like xi pi, the coordinate in the new coordinate system, and ei pi unit vector and sum over that, and pretty soon you are tired of finding all the summation. And one of the Einstein's great contribution is that get rid of all the summation. Whenever you see repeated index, in our case, it's repeated, one is subscript, one is superscript. Then you sum over there. You have a superscript and subscript, you sum, just that means you sum over whatever your number of space. In this case, 3 dimension, you just sum over 1, 2, 3. And now you just write this equal. It's okay. This is whatever they call it Einstein's summation rule. Okay, or whatever they call it, Einstein convention or something like that. Okay, so and Einstein is, I mean, just trying to save a lot of writing, and he was afraid. He liked his idea. And that actually is very good, and because when you do a lot of these things, you keep writing summation, it's just pretty soon you'll just getting tired of that. Okay, so you can write the same vector using different coordinate system, and now the idea is that you can obviously it's equivalent. The two sets is describing the same vector. So it means that all these coordinates x to xi to x prime I, all these coordinates can transform from one set of coordinates to another set of coordinates. And likewise, the unit vector, you can transform the unit vector from one definition to another definition. If you rotate it, basically there's a transformation from the old unit vector to the new unit vector. And likewise, the coordinate. And so that is the basics of a vector. So this is this position vector. And then now you can generalize your concept of vector instead of just the position vector. Any quantity that is what we call a vector will have component multiplied by the unit vector is still defined like that. But the components also transform like a position vector. And that is what we call a vector. So now you can generalize that instead of just x, the position, like take the derivative becomes a velocity vector. Velocity is also a vector, and take another derivative is the acceleration, right? And they all should transform according to the same rule. And then you generalize to conceptual thing, like you have a force between particles, and the force is also a vector, and so on. You can generalize it to many physical quantities, but they are vector if they transform like a position vector. So that's the basic idea. That's okay. So now we can now try to determine the transformation rule, and for Cartesian coordinate, that should be something that you learned before. I think also summarized in one of the sections that we skipped, section chapter 1 to 3. There should be a section about this coordinate transformation. That so we can quickly go through that in a more abstract way. I mean, if you want, you can do it more explicitly, but in abstract ways, you rotate your coordinate system, say your e to I prime, right? That must be if you express it using your old unit vector, then you can write it like the projection of this the new unit vector on the old unit vector. And the projection is what we define as the dot product. So you have EI prime, this new unit vector dot in the old unit vector, say J. Right? That's the projection of EI prime on the order. on the unit vector Ej, the O unit vector. And the vector is, this vector will be sum over all this projection in the same unit vector. This is how you define it, and then now that is sum over J, but obviously this is breaking the summation. We are not using this subscript superscript rule, but you still, for this case, for this particular case, you're still summing J and you see repeated subscript. That is the exception to the Einstein rule. Okay, and that if you write it explicitly, this is like a matrix multiplication. This object is a matrix, I and J. This is like I actually should put the pi not and the I and J is still the 1, 2, 3. EI. Put the pi on the unit vector instead. I and J is still summing from 1 to 3. Well, for this one is for a given I, you sum over J. Right? So that becomes like a matrix multiplication. Or matrix multiplied by a vector. Or matrix multiplied by a column vector. A column matrix, right? So if you write explicitly, that becomes the E. I should actually say this. Not right here. So this object. So you have E1 prime, E2 prime, E3 prime. That's given by this matrix. So the first element is E1 prime dot E1. The second one E1 prime dot E2. E1 prime dot E3. Right? And so on. Second line, second row is E2 prime dot E1, E2 prime dot E2, E2 prime dot E3. And likewise, the third row, prime dot E2, E3 prime dot E3. Okay, and then I'll multiply by the O unit vector E1, E2, E3. Okay, so this writing explicitly, this line is this line. It's a multiplication of this time. Right? You can check that it's the same. So this times that is sum over multiply this and that. And E2, E2, E3, E3, so that to E1 prime, right? Just explicitly writing it out. And that is just to illustrate that you have a matrix, and that is a matrix that we call the transformation matrix. Let me look at the notation of your text. What do you call it? I think your textbook actually doesn't. I think it's called A, right? This A trans AIJ, or not. SIJ, is an S, whatever that is. I mean, either you call it, there's also a convention because you can also calculate inverse EJ as expressed as the projection on the EI prime. But if you write it like that, that's let's just use the EIJ, the transformation matrix, SIJ. Yeah. This SIJ is a matrix that's given by that. So this SIJ is defined by this matrix. It's okay. So now you explicitly put this in one of them, put in this superscript, the second index, to that following the Einstein rule. But we don't have to. It's just make it look like you're following the summation rule. Okay, and now the next thing you can do is Next thing you can do is once you have that, the transformation of the unit vector, you can follow the same rule and transform the coordinate also, right? But before we do that, we actually, there's a property of this for Cartesian unit vector. There's a property that you can write it out and check that the Sij satisfies this property. There's plenty of space to do that. Okay, let's do it. This is here. So you can say this is this one. So you can do a dot product, the EI pi dot EJ pi. Right. And they use the same definition of same transformation to the O unit vector. So for the first one is E I pi dot already use J, then we use K. And EK, that would have an EK, but we'll write it because these are number. This is just these, all these are number. And then do the J, write down the J first. We already use K, like use L, like space, EL, right? And then there's an EK for this one, and then a dot into EL. And remember that now these are still sum, right? Because you have repeated index, so your K and K sum, L and L sum, right? And now you can use the fact that these are Cartesian coordinate unit vectors, so they are orthogonal. So the I pi dot EK and EJ pi dot EL, and that is a Kronecker delta KL. And it's okay. So this because they are orthogonal Kronecker delta, so it means that it's only 1 if K equals L, if 0 if K not equals to L. Okay, and now you can use the Kronecker delta, the sum of make one of the sum, either K or L. So that becomes a E I dot EK multiplied by E G dot EK. Right, and now you again following the fact that these are you transform the unit vector to new Cartesian coordinates. So this product, this dot product is still a Kronecker delta. This is delta Ij. Okay. So now you recognize that these two matrices multiply to a Kronecker delta, which is what we call identity matrix. So yeah, there's a matrix multiplication, except that this is in the second index. So to put it like a usual matrix multiplication, you want it to be first index, and you recognize this is our Sij. Right? Ik, this is because we define like that. This one is this one, right? And this one is Sj, right? If you sum over this K, the second index, then it becomes a Kronecker delta. So this one actually is the inverse of this one, right? But they are not. I mean, this is not exactly the inverse because I'm not putting it in the usual matrix multiplication yet. To do that, I need to do a transpose to reverse the notation of J and K. So I can write it like a space ik and call it S transpose. And then I can reverse the index, A and J. Right? And then so in that case, I actually put it. It's a complication for working on transformation matrix. It doesn't totally follow the Einstein equation. So, but anyway, I changed the order. Now this looks like a multiplication, matrix multiplication. It means the S transpose is the inverse of S. So this is at least for our case for Cartesian coordinate S transpose is S inverse. Okay, that is for our discussion. It's okay. So that will become useful if we try to get the transformation in X, but out of time. So just remember this. Now we figure out how you transform the unit vector, but I'll use this property. This one equals to that one. We know how to transform the unit vector. Then this equals to that means I can figure out how you transform the coordinate. That will be next time. Is that okay? We started by the Cartesian coordinate transformation. Basically, we are looking at this rotation between coordinate system. We're kind of like 4.1, except that we're using the position vector other than just arbitrary vector A. So I think last time we did that. So you have a vector, so you can write it like in the original coordinate system, and then you have the unit vector. And if you do a coordinate transformation, like a rotation becomes x prime prime with the new unit vector e prime I. And last time we showed the relationship between the old system, old unit vector, new unit vector, and the old unit vector is simply a projection. So you have EI. And when you got into the new old, unit vector is sum over this all three unit vector J, right? And I think the last time we showed that this matrix, whatever we call it, this Aij, whatever. And I think we showed that this Aij, the inverse of this is just like the transpose. This is right. Whatever we call it, call this Aij. Right. And that is you stop. And obviously you can, the equation 4.1 is just using this old and new linear vector and write any arbitrary vector, except now I'm using the same thing. Never mind, but this is the second rank tensor. 4.1 is using just arbitrary A vector, right? And write the component of the new unit system is basically the same, except that this is for position, but you can generalize that to just arbitrary vector. except that I mean the up to here the text hasn't introduced a superscript, what we call the contravariant, and to distinguish how to distinguish the contravariant and covariant. So the superscript and subscript are kind of not very consistent. But, anyway, but we go back to here, right? And now this is how you transform the unit vector, but then we can also transform the component. And this is a rotation, and this the coordinates are related by linear relationship. So this is so-called linear transformation. Like all this AI, a superscript I should be related to this x prime I, or by a linear relation. What we mean is this say A. So any one of them, the A1 or A2, this coefficient prime 1, prime 2, yeah, we have only three three dimensions. Okay, right. And now similarly, you have to all the components are like that. So it's I. It's the same thing, but it's different ABC obviously. But because it's linear, then we can figure out all these coefficients by simply taking a derivative, right? So obviously, if we do a partial derivative, these are called we're staying with Cartesian coordinates. So partial xi, partial x1 x1, yeah, will obviously give you a, right? But yeah, you take a partial derivative, you only operate on this one. All these will be zero because it doesn't. This is just the partial derivative means you keep other constant. In Cartesian coordinate means you are keeping x2 and x3 constant. When you take a derivative, these are just constant. You won't operate on this one. That you a, right? Okay, so then obviously you now generalize that all these coefficient calculate this way. So we can generalize this to arbitrary rotation. So like xi will be like this with just partial xi, partial x prime j, and x prime j. Okay. This we just check. This is the same. Whatever the coefficient like of the equation related xi to a bunch of these x1, x2, x3, the components, the coefficient of each term of the partial derivative of this old coordinate with respect to new coordinate is sum over all of them. So this is just like this equation, but with solving all the coefficient A, B, C in here. It's okay. So this is stick from this coming out from the linear relationship. It's okay. So we're staying with linear transform now. Then I think the next section we'll generalize that to the coordinate transform is not necessarily linear. It's basically not non-Cartesian coordinate. Even more general situation. Okay, so this is how you transform the component, right? So yeah. Yeah, this is the time coordinate, right? This is what we call the new coordinate system. So all the old coordinates are expressed as linear combination of the new coordinates. And we take the partial derivative with for the old one with respect to the new one, right? So that is this one. And this is also like a matrix. This is like a matrix, and it's in your textbook. J, yeah, J. This is J. And it's in the textbook called S. Yeah, no, textbook called this S SIK or something. SIJ. I mean, but again, the textbook is not very consistent with the superscript subscriptions because this is a superscript. This is also a superscript, but it's in the denominator, so it should be treated as a subscript. So SIJ. But this is like a matrix, right? If you write all the components together, this is a 3 by 3 matrix. Okay. All right, and now this is the coordinate. Now we can combine that to this the first equation and see that how you relate it. This one. This is a transformation for the unit vector. This is transformation for the coordinate. You can combine them and see the relationship, right? So x is xi, which is this one. So Sij, which is this one, right? And then this ei, which should be equals to no, Sij x times j ei equals to x prime I ei. Right. So now you can use this one. Whatever we did this before we discuss this. There's another matrix we call A. This A, I, J, E, J. Right. And now we can equate this one because both has the x prime. This is Sij, this is Xij, right? Aij, right? Except that I and j's are kind of interchange from here to here because the unit vector is in j. This is the component is in I, so we can. These are the sum over I and sum over j, so you can call it whatever you want. You can actually interchange the I and j. Just interchange the label. We call I, j, and j. This is j, this is I. Okay. Then obviously you see that that's A J I is implied this S I J. I keep it one is superscript, the other is subscript. But this one is kind of hard to say because it's both are in subscript. But they should be the same. Right? Compare this with that, and so obviously this is interchanging the order of that, right? So this is like the you want to compare this one, so you need to interchange that the index, right? So it becomes a transpose on the right, and a transpose also like a inverse in this case. Last time we said that. Okay, so this A matrix that transform this unit vector, and then the S matrix to transform the component satisfy this. So this is like the inverse matrix of the S matrix is the inverse matrix of the A matrix. Okay, so yeah. This one? This one? This one? This line? This line is just what, so I try to do it more explicitly from this line, right? Every component I, it can be 1 or 2 or 3, right? And each component has a relationship like that. The O coordinate is a linear combination of the new coordinate. And linear means you all the new coordinate multiplied by different maybe not, I mean, multiplied by coefficient, they can be the same or different, right? So your A, B, C, right? You understand it? This is what we call a linear relation. Now these are just constant. You want to determine this constant, and the way to do that is just taking a partial derivative. So take the partial derivative of this one with respect to like x superscript 1. That will just give you A, because partial derivative means keeping these two constant. Okay, take a derivative of with respect to x1, x superscript 1. These two are just constant. You just operate on that. That will give you just A, right? And likewise, the other ones say you want this one, you want B. They take the partial derivative of this one with respect to x2. Once you want C, you take a partial derivative of this with respect to x superscript 3, right? That is just this one. So I, whatever the I, you take the superscript 1, well, we take the derivative with respect to 1, multiplied by that new coordinate, just like this one. Like 2, you take the derivative with respect to, multiplied by the coordinate, like with this term. And the first one, give you this term. And this is a sum by the Einstein summation rule. You have J. Repeat the index in J. You're summing all 3 terms to give you this relation, give you this equation back. Is that okay? It's just writing in a more abstract way, and using the Einstein notation. This is just summing over. So there are 3 terms in here because they are summing from 1 to 3. And this is for the equation for the I component, right? I can be 1 or 2 or 3. So altogether you have 3 equations for I, and each equation has 3 terms. So it's like a matrix multiplication. This is a 3 by 3 matrix multiplied by a column matrix, 3 with 3 elements. Is that okay? It's maybe a little too abstract, right? But that's just the way to do this tensor calculation, because if you are not doing abstract notation, pretty soon you're writing like the general relativity calculation. You write everything out, it will be pages and pages of terms. Yeah, that's the Einstein notation. Whenever you see a repeated index with sum, this is just like sum over J from 1 to 3. Okay. Is that okay? It might take a while to get used to it. This is also a summation. This is just this one. I'm just calling this one. This is called S. Just give it a name. Okay. So Sij is partial x superscript I, partial x prime j. That is this one. Is writing like this is just a number, but it depends on indices I and indices j. Both are from 1 to 3, so there are 9 elements, and you can write it like a 3 by 3 matrix. So these are the 9 elements in a 3 by 3 matrix. That's it. Okay. Still too abstract. Anybody have problem with this?
So if in the denominator that was instead of in the superscript, if it was in the subscript, we will write S I J both in the superscript.
No, if both a subscript, that's a good question. If this is a subscript, this will go back to superscript. Take the derivative of no, not superscript, just sum. And later on, we'll stay with the convention that we sum only when one is superscript, one is subscript. But we are kind of in a transition from the old convention. In the old convention, we don't. So whatever you learn from the undergraduate physics, you don't distinguish superscript and subscript. Yeah, both superscript, but this is in the denominator. So effectively, when you take the derivative of a superscript variable in the denominator, that transform it to a subscript. So that is the way to look at it. Okay. We'll yeah, that is the convention. Although this is not apparent from the old system, the Cartesian coordinate, because the values of superscript value and subscript value, they are actually the same. Only when we generalize to a more general case that it will be different. Even when we work in cylindrical coordinate and spherical coordinate, that kind of curvilinear system. If you write in tensor notation, we'll have superscript and subscript. Well, okay. Stay with here a little bit. When you get used to it, you may get more comfortable with this abstract notation. Okay, so anyway, this is how you transform. So you are transforming this x. Now going back to this right here. So this is for the position vector. So x xi. Let me have order differently. This might have at the transfer of it actually. But anyway, so this is writing in. I may have called the S a different S than the textbook. This sometimes it's kind of hard to keep track of these notation. So xi in this case is partial xi. Let's write back to the partial derivative, and that is so not so dependent on the notation how you call this matrix, but just call it this is a matrix. Okay, fine, and then okay, fine. Okay, so that's how you transform the coordinate, and likewise you can the same consideration can apply to interchange the pi and non-pi, right? So you can then write if you want to transform from the non-pi to pi, the O1 to U1, and the derivative is just the other way around. This is pi. Partial x x. Okay. I think this is what the text will call S rather than this one. This is just the other way around. The derivative is one is with respect to the other. Okay, and so this is just the precision vector, but then we're requiring that any vector transform like that is what we call a vector. If any vector component now instead of x, you write any vector, you write so a, and now it's this different a. So this is like a sub I, a superscript I. Right. We write the any vector like that becomes AI. If you transform to, you choose a new coordinate system, then it becomes a component, become pi, a pi I, new vector. And then if all these component of the vector transform like a precision vector using this way, this is obvious, right? This is just the partial derivative, but any vector component, say a pi I plus 1 partial x I partial x j and that we call it a tensor. This is a tensor, and now we make the distinguishment that if you transform like that, now we're using this superscript, so that is called a contravariant vector. So there are basically two kinds of transformation. One is a contravariant, and that is for a superscript, right? And now you can also now to distinguish from this contravariant, there's another kind of transformation that you can make. That say if a vector component instead in the superscript is in the subscript, then it will transform differently. It's transform like I is in the denominator. Well, it's pi of I partial x. Right. Yeah. Yeah. This is when you write a vector with a subscript component, it transforms like that. So basically, we can also define the different unit vectors. So this is in superscript component, right? You can also write like a subscript component, and superscript unit vector, except that for Cartesian coordinate, superscript and subscript actually exactly the same. So they, but this is for general situation that these unit vector are different. The subscript and superscript will be different. But we just now right now it's just a definition. So something will transform like that. And this is like a precision vector will transform like that, and a vector transform like a precision vector transform like that. We call that contravariant. If it transforms like that, that is covariant. Okay, and so one example for a covariant vector is the gradient vector, and we use to call it just vector. We don't separate. Say we say a vector like a precision is a vector, but we take the gradient, which is a partial of the precision vector, right? And we just call it vector. We call it gradient vector, but by this transformation rule, we will see that it transforms differently. So we are done with this. Let's look at this, the gradient vector. Gradient vector or gradient of something. gradient of something. I think the text we call it phi. We call it a scalar. So the scalar is something that doesn't change. The value doesn't change whenever you rotate the coordinate system. The value of the quantity doesn't change with the change of coordinate system. We call it a scalar. Like the I component. It's just what we used to call it an I component is like partial phi partial x I. So when you take the partial derivative with this coordinate system that are superscript coordinate, that is the gradient, and this is in the I component. When we want to change it to the new coordinate system or gradient with respect to new coordinate, what we do is do a what we call the chain rule. When you derivative, you have the chain rule. Right? Remember this. This is like you want to express in derivative with respect to the new coordinates. So like you have the partial, the new coordinates. So partial k or r or j, and partial phi, partial x, which is pi j, partial xi. Right. That is the chain rule. Right. This is again very abstract. This is summation, summing of j, which means if I write it explicitly, this is partial x1, partial xi, partial phi, partial x1, partial x2, partial xi, partial phi, partial x2, partial x3, partial xi. So this is exactly like that. The sum of the j. Is that okay? No. Now you see that the gradient, ignoring this phi doesn't matter. This is the scalar. So this one, the operator partial x xi transform like this one instead of the x one, instead of this one, is transform with the matrix this one, which is what we call the transformation matrix for the covariant vector. So one example is this partial xi I transform like that. Okay, so taking derivative of this covariant coordinate, so like the xi, you take the derivative of that, remove that superscript, the subscript, because now it transforms like a quantity with a subscript. With a subscript, we transform like that, right? And this is exactly how it transforms. Is that okay? So that is one indication why we separate the superscript and subscript, right? Except of course in Cartesian coordinate that distinguishment is a little bit artificial because the superscript and subscript component are the same. But anyway, when you generalize the general coordinate system, that becomes useful. Okay, so that is a vector. Now come to the jump that we now define how you transform the superscript and subscript or the contravariant and covariant components. Now we generalize the arbitrary index, arbitrary number index, and we call those tensor. So the tensor quantity that transform like that. So now you can have any combination. So you have two superscript, like using your textbook equation problem 6. So the first one you have two superscript, I and j. Each superscript transform like a contravariant component. Because it's also x pi I, and we have already used J, so this is K, and the other one is J, XL, and L. And this is prime, this is non-prime. So if from the old one to the new one, it transforms like that. So each index, each superscript transform with transformation matrix like this one. So it's a derivative of the new one with respect to the old one. Right? Then that is second rank tensor, because second rank means we have two indices, and both are in the superscript. So this is a contravariant second rank tensor. Okay, so that's the first. I think that's the first equation, right? And likewise, you can have both in the subscript. This is the third equation in the textbook, right? Now both should transform like the other one. So x k y I l x y k c c k l. Both are in subscript. You sum over all the two subscripts with two transformation matrix, like the covariant vector. Okay, and so that's fine. So you have this is now the second rank covariant tensor. Okay, and obviously you can also define a mixed one as in I and J. Okay, when you write it like that, you have superscript and subscript, and also you write it a little bit separate. So to indicate which one is the first index, which one is the second index, because when you do matrix multiplication, all the first index and the second index is make a difference. So you need to separate. So this one you change it to I and J, like that. I in the superscript, I in the subscript, J in the superscript. That is also different. Or move the I to the second position, J in the first position. They are different also. So anyway, this is a mixed second rank tensor. So this is so the superscript will transform like the first one. Was x prime. Okay. And the second one, the subscript transform like the second line. So XL. And then B of summing over. The first one is here. Summing over K and okay. Yeah. Yeah. This is K, yeah, B superscript K and subscript L. Because you sum over L and sum over K. Right? In the transformation matrix, K is in the subscript, L is in the superscript. So you sum over only one with superscript, one with subscript, one with superscript, one with subscript. Is that okay? And so these are all tensor. And obviously you can now keep going. This is just two indices. Yeah, subscript or superscript. You can have n arbitrary n I J L M N. You can, each superscript will transform like a contravariant vector. Each subscript transform like a covariant vector. Okay, and for arbitrary number, you have n indices, then you have n. You need n transformation matrix, and it can be a mixture of different kind of transformation matrix. Okay, if they transform like that, they are still tensor. Yeah. This one, yeah, so sum over K and sum over L, because one is in the subscript, one is in the superscript, the other also a superscript and a subscript. That means the sum over 1 to 3. Is that okay? Yeah. So that's why the sum over the whatever number of space. Yes, that would be 9 terms. So sum over K, you have 3K, K from 1 to 3, L is also 1 to 3. So this is totally 9 terms in here. This equation represents 9 terms. So that's why I'm saying that if you're not using this highly abstract way of writing thing, you pretty soon writing a simple thing like that, you involve writing 9 terms out explicitly. And special relativity, these are just 3 by 3. In special relativity is 4 dimensions. So it becomes this becomes 16 terms instead of 19. No, that K, they can be any number. So K can be 1 to 3, L can be 1 to 3. The total combination is 9 possibilities, right? Like 1 1 1 1 or 1 1 2 2. Is that okay? So altogether nine terms. And in this case, I and J are fixed because you're talking about this particular element, how you transform, but this element. So this element, when you transform this element, one element in the new coordinate system, I and J, ij element involve the combination of these all element, 9 of them, right? And then you need to do all these summations. So altogether you have 9 terms. You write it explicitly out, that becomes 9 terms. Is that okay? So again, quite abstract, but it's useful because if you're not doing that, you're just spending all your time writing terms out explicitly. Is that okay? And that is becomes a criteria of tensor. So only quantity that transform like that tensor, either covariant or contravariant tensor, doesn't matter. Those are still tensor. Okay, but they have to transform like that. And the reason is that we want to write physical law that geometrical object. It means that it is intrinsic. It has intrinsic property that not dependent on our choice of coordinate system. If we choose a different coordinate system, then the equation all change. Then it's not good, right? If you write that your physical law in terms of tensor operation, like tensor add to tensor and tensor multiplication, then the physical law will not change, right? And now we can show that by defining all these tensor operation. Clearly, the addition and subtraction is trivial. The text will just give a trivial example: a plus b. All these are tensor of a base c. Then this equation, the form of this equation will not change whether you are in the new coordinate system or the old coordinate system, because all of these is transformed accordingly. And so that, and all this transformation you can add to addition. So obviously, if they are the same kind of, they are the same kind of object before you can add that. So you cannot add a second rank tensor to a scalar. That doesn't make sense, right? So in your case, or contrary, then you can add them or subtract them, and they transform like that. But if they are not of the same natures, like if this is ij, this is I, one is in the subscript, one in the superscript, then you cannot add the two, right? Because that will not transform. This term will not transform like this one, right? Because one is transformed one way, like this one, the other transformed this way, right? Then you cannot write a physical law with this kind of equation. Okay, so the same kind of tensor, when you add them or subtract them, they have to be of the same nature. Okay, so that one restriction of your physical law, how it depends on physical quantity. And there's discussion about symmetry. I think it's when a matrix symmetric. I think you learn all these supposedly. The matrix is symmetric. Symmetric is this is exchange the indices is the same is symmetric. If it has a negative sign, if you exchange the index, it has a negative sign, becomes anti-symmetric. Yeah. Yeah. You can see that, but the text will call anti-symmetric. Yeah, that's fine. And any matrix can be separated into one part is symmetric, the other is anti-symmetric. So that is fine. Okay. All right. So that is something that is supposedly know all these matrix things. Okay. And now the next example is give an example of this tensor. This conic delta, right? And how the conic delta transform. So, it depends on which equation you want to write. Because obviously, if you write define derivative, say, or this component, whether it's the O1 or new1, xi, and also x2, right? So we talk about this the position component transform like a contravariant using the contravariant transformation. When you put it in the derivative, the derivative of the gradient is covariant. Now, if you do a derivative like that, obviously there's one in the superscript, the other in the subscript. This becomes a mixed tensor because you have I component, J component, and by the simple rule that taking derivatives, obviously this is just conic delta. But you want to write it like one is in the superscript, the other in the subscript. All right, so that is this one, and you want to see how it transforms. So how that one transform, and to do that, this is in the the O coordinate, so the new one, so partial x prime partial x j, right? That is x prime over prime. Obviously, this is just comparing this. This is just delta, conic delta in the new coordinate system, and now we want to see how it transforms. How it transforms the O1 to the new one, right? Then what we can do is like a chain rule of that. So like what this one, so partial x I. We use j, we partial x k, right? And then the derivative of this is becomes partial x k. Right. We want to get derivative with respect to x summing over the chain rule is k or j partial x j. Yeah, partial x prime. Right. And now the what we can do is x prime I, x k, x, and we can multiply by a constant delta with here and then change x and exchange that to conical delta, because the conical delta basically, if you sum over L, then L becomes K. Right. All right, and that is like a transformation, because let's look at this and that one. So there's a superscript I, right? And transform using the contravariant compare with this one. So using the contravariant transformation matrix with the sum over K with the O conical delta, right? And then that is the subscript J transform like the covariant one, like this one, right? This one, the second matrix, second one, this one. So this one is transformed like this line, right? This is mixed matrix, mixed second rank tensor. Obviously, they are actually the same, like the value-wise, because all these are defined as if I and j not equals, they're 0. If I equals to j, they are 1. So basically, in all coordinate systems, they are the same, but they also transform like this. Right. Okay, so this an example of a tensor, which is now is a second rank mixed tensor, is a conical delta. Okay, now go back to this operation. So obviously, physical law will require that. Yeah.
I think the just like the one we have up there.
Yeah.
That does transit to the equation somehow. So like we have the partial derivative of x I prime, then 1, that will give us a quick delta, was introduced new one. So sorry, I'm not understood that.
This mean what this line mean? Yeah, you're asking about?
Okay, there's another variable coming in.
Yeah.
And the initial the left hand side is not existing.
The left hand side is what?
The left hand side is the delta prime.
The left hand side is this one. This one equals this equals to this. Equals to this. This from that is I just introduce this conical delta to change K to L. Yeah. Yeah. Okay, and now the other kind of operation with respect to tensor, the contraction. So when you write in physical law, then you can do this contraction. Let's see what. The simple one is the contraction between two vectors. So let's just so if you have a contravariant vector, so text is A and B. A and B. Yeah, you have a contravariant vector A is A I, and the covariant B. Then you can do a contraction what we define as this dot product. It's now involving just sum over them because the summation rule one is in superscript, one is subscript, then this is A I. Okay. Right. Oh, A I B I, meaning sum. So there's three terms. A I, this I. Okay. And now we want to show that this is this definition will give you a scalar. So once you sum over that, that doesn't have any index left. That means it's a scalar. Scalar means it doesn't change the value. So we can now substitute this transformation and check that. So this one. So it means in the both the old and new are the same. Meanwhile, after you transform to a new coordinate system, the dot product doesn't change, which means it's a scalar. Okay. Now we check that by using the transformation rule. So this A prime I is partial X prime I of X K, and then A is K, and then B prime is using the subscript. So also X prime. No, that's XK. XK is also X prime I and BK. Okay. And now you can group these two together and then realize that this is just what we erased. This is the conical delta because this is like a chain rule. So partial X prime. Now it becomes partial X prime.
A of W. It's an A of this. The A of this.
Yeah, that's a A. Yeah. Okay. Right. Now the chain rule becomes because it depends not because there's two summations. You can like sum over I becomes partial xk is partial xk. Okay. Oh. I. But this is AI prime. This one, that's sum over. I think I make and this you should use the same. This should be L. That is more like L, right? This is L. XL. Okay. 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 Now this is a conical delta. This is delta L. Okay. And now you can use the conical delta to change k to L or L to k. Doesn't matter. Which is just like that. So this one equals to this one, which is this one. Okay. Now by the explicit transformation rule for contravariant and covariant component, you show that you define a contraction like that, then the form of the equation is unchanged, and that is why that is what we require of physical law, physical quantity. So we are using physical law to describe quantity that the form doesn't change with respect to our choice of coordinate system. Okay. So that is contraction between two vectors, and then you can generalize that to any component. Doesn't have to be between vector. You can tensor contract a component, a tensor with respect to a vector like that. Say if you sum over, so you have a Aij second rank tensor, you can sum with a covariant vector, and what is left is a contravariant vector because you sum over the superscript and subscript. Basically, what we call the name is contraction. Contract the superscript and subscript. What is left is just one superscript. Becomes a contravariant vector, and you can check that by the same way. Just substitute this the transformation that this you do the transformation, then a prime and j prime and from C, how you transform some Ci, C superscript I and C sub j is following the same rule as contravariant vector, and this object also transformed to this according to the same rule. And you can check that just like what we did here. Anytime you do a subcontraction, basically this is saying you preserve the form of the equation. And you just do a coordinate transformation. Originally the equation is like that. After you do the rotational coordinate system, the equation is like that. So the form is exactly the same. Okay. So, yeah.
I think that sequence should be
Yeah, you're right. Okay. What else? But this is one kind of part of the contraction, and it will reduce the number index. In that case, originally you have a second rank and then multiplied by a vector, the first rank, and reduce the second rank, first rank. We reduce the index by 1. And yeah. Yeah, sometimes it's like that. I might not have been too consistent. And for the conical delta, it doesn't matter because it's a symmetric matrix. Conical delta is a symmetric matrix, so it doesn't matter that much. Yeah, sometimes it could make a difference in the form. Yeah, because the matrix multiplication involves the position of the indices. Sometimes we have to be a little careful. If you look at it like a matrix multiplication, but when you do a summation rule, then the order doesn't matter that much. If you forget about all the matrix multiplication, not treating it as matrix, just treating it as summation using Einstein rule, then the position doesn't matter that much. But if you want to transform it to a matrix multiplication, then you need to be really careful. Just the way how you define matrix multiplication. Yeah. Yeah, when you do a summation, obviously these are just number, or like a summation. This one, or you are you asking me why you like that? Is that okay? Yeah, that's fine also. I mean that this is a symmetric matrix, so whether you put it in front or not, that doesn't matter that much. And also, I mean, it matters when you try to transform an equation to a matrix equation. That you need to be careful. Okay. If not, if you're just doing summation rule, then it doesn't matter because all these are just numbers. All these are just numbers. If you forget about they can be represented by matrix, you can just treat it like number and just sum over them. Okay, so that two ways of looking at that. And I mean, matrix multiplication has an advantage. If you put it in a matrix, then you can use some of the what you learn in matrix multiplication. But if not, you just treat it like a summation. The different kind of product is this direct product. Basically, it's just now it's just multiplied tensor with different indices. Like in the textbook, we have a mixed matrix, a mixed tensor, B, J, L, M, and now this is because they are all different. That product you can still do a product like that. So this is still a tensor, and then it has two superscript I and J and three subscript K. Like, now the order doesn't matter that much because this is so high rank, so you probably don't want to do a matrix in such a high rank situation because it doesn't give you any advantage. Look at it like a matrix. Okay. And so again, physical law can involve direct products also. They are just fine. Yeah. I, J, K, L, M, yeah. Not what? I mean, you can look at it like element. This is fifth rank. So you have this is a really large element. See, what do you call it? A fifth rank tensor. So it's a high, you cannot even think of it. So second rank is a square, right? Third rank is a cube. Fifth rank. It's not 5 plus 5. All these are 1, 2, 3. All these are 5, 1, 2, 3. So a vector is 3 elements, right? You have 1, 2, 3. Then the second rank is a 9 element. 2, 3, 4, 5, 6, 7, 8, 9. And then the third rank tensor, you can still geometrically look at it like a cube. It's like extra dimension. Here's a cube. And then the fifth rank is whatever hypercube in 5-dimensional space. So when you get to high order, sometimes you look at it like a matrix. Doesn't give you advantage. Okay, you can just look at it just like a number. Is that okay? Just element. I'm just saying, why any third rank tensor you have 3 elements. Yeah, a column vector. A column vector is a matrix in. Yeah, all these ij's are three-dimensional index. So I is from 1 to 3, j is from 1 to 3. So they are all the same. They are all indices from 1 to 3. Yeah. So if you don't look at it like a matrix, that's just a number. Just a number that depends on ijkl, and ijkn can take, each one can take the value of 1 to 3. So altogether is 3 to the 5 power number of terms in this one, right? Is that okay? So 3 to the 5 number of different terms for this tensor, fifth rank tensor. Is that okay? So, okay.